Emily, are you ready?
Yeah, ready whenever you are.
So everybody can see my screen well?
Yeah.
Okay. Hello, good morning, good afternoon, and good evening. This is Paul Liu from NC State University, and welcome again to the World River and Delta System, the Source to Think webinar series. And today we invite Amelie Paszkowski from University of Oxford, UK, come here to talk about geomorphic change and the risk dynamic, the case of Bangladesh study. So this webinar series is co-sponsored by NSF, NC State, Louisiana State, East China Normal University in Shanghai, Utrecht, Netherlands, and the CSDMS. So as always, all the talks have been archived on our YouTube channel. So also on the Bilibili station. At the same time, we are maintaining Source to Think Twitter account. As you can see, we will announce every weekly talk, any news, publication, any related information. So next week, next Wednesday, same time, we have a talk given by Jia Wang from Utrecht University, talk about spatially explicit nitrogen and phosphorus import to the Chinese Sea, the marginal sea, the implication for coastal ecosystem. And so, as I mentioned, Amelie, she is currently a PhD student working on the dissertation, and today's topic is basically the same topic about geomorphic change and the risk dynamic, the case of Bangladesh. Her research is mainly focused on the geomorphic hazard with society dynamics in Bangladesh. So Amelie, now I'll give the floor to you. You can share screen and for the presentation mode. Yeah.
Yeah, thank you so much. Can you see the screen?
Yes.
Great. Thank you so much, Paul, and thanks a lot for having me here. Yes, as Paul mentioned, I'm Amelie Paszkowski. I'm a PhD student in Oxford, and my PhD aims to bring together the geomorphic processes in Bangladesh into our understanding of risk dynamics, with this country being my main focus. So today, I'm talking mainly about a recent publication on geomorphic change in the GBM Delta, but also we'll be talking about the other aspects of my PhD, which I've been working on since then. So as most of you probably know, Bangladesh is the most downstream nation of the Ganges and Brahmaputra rivers. These rivers drain approximately 75% of the Himalayas and discharge the highest amount of sediment into our oceans than any other river system in the world. And around 80% of Bangladesh is made up of tributaries and distributaries of the GBM system. And given its deltaic landscape, it's an extremely flat country with around 2/3 of Bangladesh being below 5 meters above sea level. So this combination of an extremely high density population with 165 million people living in this country, combined with this low-lying lands, have made Bangladesh one of the most vulnerable countries in the world to natural hazards and sea level rise, which is very clearly indicated in this map on the slide you see here. And although the country's vulnerability to risk is widely acknowledged, it's extremely rare to see the inclusion of geomorphic hazards in this understanding of deltaic risk. And here I define geomorphic hazards as landscape changes that affect human and environmental systems. And these hazards include things such as riverine and coastal erosion, channel siltation, or land subsidence, which can either directly impact populations in the environment, or it can also exacerbate the vulnerability of populations to other natural hazards. And given that deltaic nations like Bangladesh are in a constant state of geomorphic flux, this lack of inclusion of geomorphic processes in our understanding and interpretation of risk is particularly concerning. And it's led to large-scale human interventions being implemented and then undermined by unanticipated geomorphic responses, which have resulted in a significant series of economic and environmental costs. So I will be using the IPCC definition of risk, which is the combination of hazard, exposure, and vulnerability. And we'll be using this framework to guide this presentation. So firstly, I'll be looking at the hazard component. And in this section, I'll be presenting the recent publication in Nature Reviews, Earth and Environment on the geomorphic evolution and current dynamics in the GBM Delta. So this is the main part of the presentation. And in this section, I hope to convey the message that these geomorphic processes really should be considered as hazardous, as they really can have significant impacts on our environment and our societies. The next part of the presentation will focus on the element of exposure. So this is a paper I'm currently working on, which looks at the number of people exposed to geomorphic hazards in Bangladesh and the associated poverty dynamics in these regions. And then finally, I'll be looking at the vulnerability component through the lens of resilience. So this is another paper I'm currently working on. And this part of the presentation will be rather brief, but we're basically zooming into some riverine communities in Bangladesh to assess their resilience to hazards. So starting off with this first component, so this paper was published in October together with Steve Goodbread from Vanderbilt University, Eduardo Borgomeo from the World Bank, and he's also in Oxford, Mohammed Shah Alam Khan from the Institute of Water and Flood Management in Bangladesh, and Jim Hall from the University of Oxford. So this is a review paper bringing together our current understanding of geomorphic change in the GBM Delta, and now I'll just be providing an overview of the main findings from this paper. So when I embarked on this journey, this PhD journey, basically one of the main things that I was interested in is how delta morphologies can adjust and shape themselves in response to environmental and anthropogenic changes. And I strongly believe still today that the future sustainability of delta systems really does require a very detailed understanding of how delta morphologies can adjust and are linked to these different processes. But when starting the PhD and reading a lot of the literature in the GBM system, what I was finding was that the literature was quite temporally and spatially scattered. So there was a wide range of studies assessing the historical formation of the GBM Delta throughout the Holocene period. And then there were some more studies focusing on more recent trends that tended to be more localized, assessing geomorphic processes in different parts of the Delta. But this system-wide understanding of bringing all of these different pockets of knowledge together was still kind of missing. And on top of this, what I was also finding was that there was quite a lot of disagreement on some of the key elements, key geomorphic elements of the GBM system. So there were disagreements on how much sediment was actually, how this sediment was being deposited across the deltaic landscape and the predominant mechanisms that drive geomorphic change in the delta. So for example, some studies were suggesting that the GBM delta is a stable delta system that is actually still growing and prograding into the sea, whilst other studies were suggesting that it's one of the world's sinking deltas. So these types of inconsistencies create confusion and can also result in these processes just being ignored entirely when we start talking about deltaic risk, because there's this lack of understanding of what's actually going on. So in order to address the scattered nature and the inconsistent understanding of geomorphic processes in the GBM Delta, the aim here was to bring all the existing studies together and map them out and link them across the literature space. So we do this by applying a systematic literature review, where we undertook a multi-staged screening process, narrowing down an initial set of 3,000 articles to 427 relevant studies. And then in order to kind of organize those studies and categorize them, we apply the DIPSIA framework, which is the drivers, pressures, states, impacts, and responses framework. And this basically provides a holistic, full picture of where the majority of scientific attention is centered. So here in the Sankey diagram, you can see the spread of literature. And just a note, if a paper looks at multiple processes, then it's represented multiple times in this diagram. So you can see in the Sankey diagram that the majority of scientific attention is really focusing on these natural drivers and anthropogenic pressures, with a lot less attention on how geomorphic changes actually impact society and the environment, and how people have been responding to such impacts. And this finding actually plays a key role in why geomorphic hazards could be ignored in risk analyses, because if we lack this clear understanding of the full extent of impacts that these processes can have on our societies, then we can't add the weight that these processes need in order to be incorporated into our risk assessments properly. So we use this DIPSIA framework as well in the paper to kind of synthesize the understanding. So I'll be using it now in the presentation, starting off with the drivers and pressures of geomorphic change. So here you can see along the top, the main drivers in the main changes in the geomorphic states, with the main drivers and pressures along the bottom of the timeline. So you can see on this timeline that the GBM delta was created through the interactions between plate collisions and sea level rise, where a rapid level during the late Cretaceous period and early Quaternary period was an efficient way of trapping riverine sediments, and then started the construction of the delta. And then later during the Holocene, the rate of sea level rise slowed by an order of magnitude, and that slowing in sea level rise enabled the sediment to be deposited and allowed the delta to prograde further into the sea. It is also worth noting here that the Ganges and Brahmaputra rivers used to flow separately into the sea. And then due to subsidence, earthquakes, and gradual tectonic processes over time, the two rivers met around 200 years ago and have been flowing into the Bay of Bengal together since then. And if you look at the right-hand side of the timeline, you'll see a lot of yellow dots, which shows that during the last century, the main drivers that have been changing the geomorphology of the delta have been anthropogenic. And these types of interventions have included large-scale changes such as river diversions, upstream dams, excavations of canals, land reclamation projects, and the polarization of the coastal zone. All of these have had massive impacts on the morphological equilibrium of the delta. So as an example, in the 1960s, the coastal region of Bangladesh was embanked to form 139 polders as part of the Coastal Embankment Project, which aimed to protect communities from flooding and boost agricultural productivity. These embankments also, however, disconnected the rivers from their floodplains and have prevented tidal and fluvial sediment from infilling these embanked lands. So what this meant is that with the sediment now no longer being able to be deposited on the floodplains, it was being deposited within the channels. And so a lot of channel silting up has been observed, and an increase of sediment deposition further into the bay as well. In 1975, India completed the construction of the Farakka barrage on the main branch of the Ganges River, which diverts approximately 60% of the dry season flow to the Hooghly River towards Kolkata to make the Kolkata port navigable all year round. And although this is beneficial for the Indian coastline, it's also entirely changed the landscape of southwestern Bangladesh. Some channels have completely dried and silted up, and the dry season salinity front has moved progressively more inland and has increased in the southwest of Bangladesh by an order of magnitude, which has had a big impact on the health of the Sundarbans mangrove forest. And then since the 1980s until today as well, more and more Bangladeshi farmers are converting from rice farming to shrimp farming, which has further exacerbated its salinization problem in the southwest of Bangladesh because more saline water is being invited into this environment. So you can see from this overall timeline that the deltaic dynamics that we see today are a real complex mixture of background natural processes that are responding to long-term change, as well as shorter-term responses to quite significant anthropogenic activities. And then we move along the DIPSIR framework to look at the current geomorphic states in the delta, and I'll just focus for the purpose of the presentation on two main geomorphic states, the first one being sediment influx and distribution. So as many of you know, the influx of sediment to a delta system is the only real natural mechanism that allows it to sustain itself above sea level. So it's quite alarming that the literature is in disagreement about how much sediment is actually entering the GBM system and how this is distributed. But these disagreements are mainly linked to the fact that each of the studies have different methodologies, different locations of where sediment is being measured, which also means that a different area is included within the assessment. But by bringing all of these studies together, we here provide the first kind of spatial sediment source to sink picture for the GBM delta, which focuses on proportional distributions of sediment rather than actual quantities, because there's more disagreement on the actual quantities, and those are also a lot more sensitive to seasonal and temporal changes. And this kind of picture of the sediment source to sink for the system is really exciting to me to have been able to do this. And it's also really important for sediment management plans, especially those that are currently being discussed, where they aim to tap into these natural sedimentation processes to enable the growth of land in the coastal region. And then when we look at subsidence, the patterns are also very interesting, with the long-term and deep background subsidence being natural and widespread. And this natural subsidence is varying between 0 and 4 millimeters per year, mainly driven by isostatic adjustments, sediment compaction, and changes in sediment distribution patterns. But then you can also see these small hotspot areas of subsidence of up to 43.8 millimeters per year. And these shallow subsidence values are mainly around urban centers where there's an increase in groundwater abstraction, as well as in the poldered coastal area where this disconnection between rivers and their floodplains have exacerbated subsidence at a localized scale. And then these changes in geomorphic states really have a whole wide range of different impacts, including an increase in flood risk, reduced navigability in the dry season, loss of land to erosion, increase in soil and groundwater salinity, arsenic contamination, habitat and species endangerment and extinction, loss of livelihoods and ecosystem services, people's displacement, and also an increase in poverty. There are millions of people that are at risk from the impacts of erosion across Bangladesh. Most of these impacts are occurring along the Jamuna River corridor, which is the lower Brahmaputra River, where more than 870 square kilometers of land has been lost since 1973. And in that same period, only 117 square kilometers of new land was created, which means that the river is consuming 7 hectares of floodplain land for every hectare that it can create. And the livelihoods of these riverbank and river island dwellers are persistently impacted by this erosion, because when their lands, when the river captures their lands and their homes, they tend to relocate to equally as exposed areas. And so it's a repeated process of the river continuously capturing these people's homes. So some riverine dwellers along the Jamuna River have had to migrate on average every 6 years. And changes in geomorphic states and the shifting lands also means that flood risk can decrease in certain areas of the delta, but also increase in other areas. And most notably, the pluvial flood risk, so rainfall-induced flooding, has increased in the poldered area of the coastal zone. So this picture from Sally Brown and Robert Nichols that you see on the top right-hand side here, if you imagine the land behind there is so much lower than the level of the river, and then you have a monsoon rainstorm falling onto that land, where is that water going to drain? So we have basically a whole area of a waterlogging situation where drainage congestion has become a huge problem. And then there's also the problem of when these embankments are broken or breached or overtopped. When this land behind the embankment is so much lower, that risk to devastating flooding is a lot higher. And I kind of touched upon this earlier, but this increase in saline intrusion in the southwest of Bangladesh is one of the leading drivers of biodiversity loss in the globally important Sundarban mangrove forest. So the extent of the mangrove forest has remained stable, but around 25% of the forested area has experienced an overall negative trend in biodiversity. And this is likely due to the dieback of the more freshwater resilient mangrove species, which are struggling to survive in the ever more saline environments. And then for the last stage of the DIPSIR framework, we focus on how societies have been responding to these geomorphic processes. So we put together a table of example responses that are currently being discussed. And these range from engineered measures to individual farming responses. And then we rated them based on cost, flexibility, technical feasibility, and social acceptability, which are categories in line with the Bangladesh Delta Plan for this century. So some of the examples here include upgrading of existing polders and elevating these embankments, mangrove afforestation along the coast, reintroducing the local bandol structures, which are made from locally sourced bamboo and help to stabilize the smaller scale riverbanks and tributaries and distributaries, and adjusting livelihoods, such as creating floating agricultural beds that are more resilient to fluctuating water levels and eroding banks. So finally, the paper then discusses some of the key knowledge gaps after assessing the existing literature base in the field. But today I just wanted to highlight the knowledge gap that I feel is the most important one, or the most frightening one, I guess, which is the spatial and temporal focus of these studies across the whole literature space. So you can see in this figure here that most of our attention is focused on the last few decades, which is understandable because that's where we have most information and data. And then there's this other nucleus of studies around the Holocene period, where studies have been looking at the evolution of the delta using various different dating techniques. But there's these two key gaps here in our temporal understanding at the centennial scale and into the future. And as most of our infrastructure systems have a lifespan of around 100 years and are being implemented today and in the last few years, these will have huge impacts on how the deltas behave in the future. So this is alarming that at these two scales, where the scale of infrastructure systems and the future are the two areas that we really don't know enough about. So it does put into question how we can actually prepare for sustainable deltaic management if we don't really know much about those two timeframes. And that's particularly concerning when the future is looking like this, where Francis Dunn and colleagues here have shown that there's 414 dams planned within the GBM catchment, some of which are already under construction. On top of all of these dams, China is also discussing a south to north water diversion project, which would aim to divert 200 billion cubic meters of water from the Yarlung Tsangpo, which is the upstream Brahmaputra, towards the Yellow River in order to increase the hydropower generated by the Yellow River. And on the other side, along the Ganges, India has also got plans to link 44 of its rivers with 9,600 square kilometers of canals, which would also dramatically impact how much water and sediment is being delivered to Bangladesh. So, the sustainability of the GBM Delta here you can see is much more influenced by this direct control of regional management programs and decisions made upstream. And we really do need more research focusing on how the Delta might respond to some of these dramatic changes. So concluding this first chapter on geomorphic hazards, I hope I've convinced you. And I hope that the paper also illustrates that geomorphic processes really are fundamental in shaping the delta and play a fundamental role in either exacerbating risk or enhancing sustainability. And also that these processes are extremely sensitive to human interventions. So we need more open and data-driven water and sediment dialogues amongst all the governing bodies if we want to achieve more sustainable deltaic management. So I've also provided the link here in the slide if you're interested in the paper. I'm also very open to any suggestions, any comments, so please do share your thoughts on the paper if you do get a chance to read it. So that wraps up the first part of my PhD and this presentation. And now I'll just talk a bit more about some of the bits I've been working on since then. If you remember the first Sankey diagram I showed, one of the main gaps that Sankey diagram also illustrates is that we don't really have a good understanding of the full extent of the impacts of these geomorphic processes. So for this next bit of the presentation, I'm building on that first paper that I spoke about, and I'm briefly going to go over this finalized paper now, which looks at the exposure of populations to geomorphic hazards, and then the spatial poverty dynamics within those regions. So for this piece of work, I've been working in collaboration with Timothy Tigeloven from VU Amsterdam and Eduardo Borgomeo and Jim Hall from Oxford as well. So as you are all probably aware, Bangladesh is known to be a country with high rates of poverty, but it's also seen an impressive reduction in poverty in recent years. And now around 20% of the population is living below the national poverty line of $1.9 a day. And the Bangladeshi government also has ambitious plans to eradicate most poverty by 2033 and all poverty by 2050. And some of the key policy documents for the GBM Delta and for Bangladesh, such as the Bangladesh Delta Plan 2100, have acknowledged that geomorphic hazards such as river and coastal erosion can really act as key drivers in furthering poverty. But until now, and as far as I'm aware, there is no spatial understanding of exactly how many people are exposed to these hazards and how do these hazards actually link up with poverty dynamics in Bangladesh. So in this study, we spatially quantify the population exposed to geomorphic hazards and assess how this exposure propagates across different wealth groups. And as far as I'm aware, this is the first time that geomorphic processes are being linked with poverty and societal welfare anywhere in the world. So I'm very excited about this piece of work, and I'm looking forward to getting it finished as well. So we use the deep water map model to detect geomorphic hotspots across all of Bangladesh, which is fully based on satellite imagery. And here we show this map of high resolution spatial understanding of geomorphic change across all of Bangladesh. So this is built on Tess Hariel's work in 2020. They applied this model to the GBM Delta, but this is the first time that it's done at the national scale for all of Bangladesh. And the results here show that 28,300 square kilometers of land in Bangladesh is geomorphically unstable. And that's equivalent to around 850 square kilometers each year. Of that, 38% is either eroding or subsiding, while 62% seems to be accreting or drying up. And as you can see in this map, the majority of this geomorphically dynamic areas are within the river corridors of the Jamuna, the Ganges, the Padma rivers, and also in the Meghna estuary. There's also widespread waterlogging that is evident in the blue region in the southwest of Bangladesh, and a lot of drying up in the Sylhet Basin. And although these findings have been extremely interesting for me, I've also really just enjoyed zooming into some of these river channels and admiring how beautiful these planform changes are. They just blow me away. But then getting to the point, so we look at exposure and calculated that just over 22 million people are living within these geomorphically hazardous areas. And this figure has grown by 5 million people in the last 20 years. So when looking at this spatially across all of Bangladesh, we see that the greatest relative increases with respect to population density are occurring in the eastern divisions of Sylhet, Dhaka, and Chittagong, followed by the northern districts of Mymensingh, Rangpur, and Rajshahi. The greatest absolute increases in exposed populations to geomorphic hazards are seen in the Dhaka division, where there's been an increase of 1.7 million more people in the last 20 years. But this is also, I guess, expected because this part of Bangladesh is the most densely populated area. And then when we look at some of the spatial poverty dynamics, so here we're using the DHS wealth index, where the wealth index ranges from -2 to 2. So here in Bangladesh, it ranges from -1 to 2, with -1 being extreme poverty, and anything below 0 is in poverty. So here we can see basically that in these geomorphically unstable regions, which are kind of highlighted you can see within the river corridors, and then within each district, you can see the distribution of the population. And of the 22 million people that are exposed to geomorphic hazards in Bangladesh, 85% are living in poverty. So with a wealth index of less than 0, and 40% are living in extreme poverty. And when this is compared to Bangladesh overall, we can see that the extreme poverty quartile of -1 makes up 20 to 22% of the population in Bangladesh, whereas it's double that in the geomorphically hazardous areas. So this again kind of reiterates this point about the fact that the poorest portion of the population is living in these geomorphically hazardous areas. And another interesting thing to note on this table is these growth rates. So you can see that the growth rate across the 20 years of assessment is relatively similar between Bangladesh and the geomorphic hotspots for the lower 2 wealth quartiles, but in the upper wealth quartiles, there's more of a difference. And this basically is suggesting that because of the impacts that these hazards can have, the people that live within these exposed areas are likely to be trapped in this poverty cycle where they cannot escape poverty because they keep getting impacted by these different types of hazards. And this is also diagrammatically represented here in this histogram, which when normalized clearly illustrates this shift here in the population's socioeconomic structure between the population within geomorphically hazardous areas compared to Bangladesh as a whole. And in order to test whether that shift is statistically significant, we performed the Mann-Whitney U statistical test, p-value of 0.03. So this basically concludes that this shift we see is statistically significant. So these millions of people that are facing erosional hazards, particularly on river islands and riverbanks and coastlines, are very likely to face relocation as their land is either temporarily or permanently lost to the rivers or the sea. So it's very different to flood hazards where you you can decide whether you want to stay and cope with flooding or whether you leave. With erosion, you don't really get that choice. Like your land is gone and it might come back, it might reemerge from the river and you can reclaim it, but you still are inevitably going to relocate either temporarily or permanently. And this kind of happens on a repetitive cycle because, like I said earlier, these populations then tend to relocate to other charlands, so other river islands, or on the same river island that is equally as exposed to these types of hazards. So they relocate and then it happens again, and then they relocate and it happens again. And so it's really difficult for these communities to actually escape poverty because it's a continuous cycle where they keep getting pulled back. So this study kind of shows that the current and future disaster risk reduction measures and poverty reduction policies really need to be aligned and need to be addressed in unison and take into account for the importance of geomorphic change. The polarization of the coastal zone was a past example that did try to target both. So they aimed at both reducing the population's exposure to riverine and tidal flooding and simultaneously also alleviate poverty by boosting agricultural productivity. But without adequate incorporation of geomorphic processes, the effective protection of these polders to hazards has been undermined, and in some areas, exposure to hazards and poverty has actually increased. So now there's a whole range of other projects, including the Coastal Embankment Improvement Project, smaller scale tidal river management projects where embankments are breached on purpose, and other localized projects in the coastal area of Bangladesh that are aiming to basically implement more dynamic measures that are able to accommodate for these changing processes. So with this study, we kind of were hoping to highlight the socioeconomic importance of geomorphic hazards in order to kind of give that weight and make these geomorphic processes more commonplace and more mainstreamed in decision-making and future assessments of deltaic risk. So finally, the last part of the presentation looks at the vulnerability side of things. And here we are looking at, we're zooming into some of the most poverty-stricken and exposed populations that were identified in the previous section. And then we assess how these communities have actually been coping with riverine hazards, which include flooding and erosion, and what levels of resilience these communities currently have. So this again links with the Sankey diagram at the beginning, which also identified that there's very little understanding of how people have been responding, of how people have been responding to geomorphic processes and impacts. So here we basically focus on that and provide this systematic quantification of resilience in riverine communities in Bangladesh. So for this piece of work, I've been working in collaboration with Finn Laurian and Reinhard Meschler from IASA in Austria, and Jim Hall again from Oxford. He's my supervisor, as you can tell. And so, yeah, in this case, I guess the main thing that is worth noting at the beginning is just this fact that disasters are felt at all scales, but really most acutely, rural resource-dependent communities are extremely sensitive to environmental changes. So this is one of the reasons why I really wanted to focus at the community scale for this last part. So many studies, including my previous section of the presentation, have shown that riverine communities living along the riverbanks and river islands in Bangladesh are amongst the poorest and most vulnerable populations. But this notion of vulnerability has also been disputed by other studies, which basically argue that people have been living in these areas for generations and they've been able to cope with riverine hazards. They've adapted their livelihoods to remain flexible and resilient and basically able to adjust to these constantly changing environmental conditions. So while this debate is kind of going on in the literature space, there hasn't really been a systematic approach of quantifying community resilience in Bangladesh. So here we are defining resilience as a combination of absorptive capacity, which is where you cope with the impacts of the hazard time and time again, combining that with adaptive capacity, where you're incrementally adjusting to change, and transformative capacity, where it's more about the long-term changes. So transformative capacity at like an individual or a community scale would be something like a change in your livelihood or your location. So for this purpose of the study, we're looking at 35 riverine communities across Bangladesh, covering a total population of 71,000 people. These were selected by local NGOs, and they base those decisions on the communities as high flood and erosion risks, high levels of poverty, and resource-dependent livelihoods. So basically, these are the worst case kind of situations. So on average, across the 35 communities, 47% of people are living below the national poverty line, and 80% of livelihoods are agricultural. All of the communities experience flooding every year, with the majority of communities experiencing 40 to 60% of complete inundation of their communities every year. And of those 35 communities, there's also 26 that are within geomorphically hazardous areas, with 19 communities in highly erosive areas. So this diagram here shows our approach, which is using the FRMC tool. So this is the Flood Resilience Measurement for Communities tool, which was developed by the Zurich Flood Resilience Alliance. And that's a collaboration between academics, which include EASA, NGOs, and insurance company risk engineers. So the tool comprises, you can see on the left-hand side, that the tool comprises of 44 discrete indicators called sources of resilience. And these are measured before and after disaster events. So each source is graded between A and D. And the data that's used to inform the grading is collected from household surveys, community and focus group discussions, as well as secondary data. So for the purpose of this talk, I will just skip over a few bits and jump straight to the measurement of resilience and some of the strategies that communities are putting in place to manage their future risk. So in order to quantify the overall level of resilience for each community, we are applying the 5 capitals analytical lens, which includes human, social, physical, natural, and financial capitals. And by applying this analytical lens, this kind of tells us how the communities distribute their efforts in order to enhance their resilience. And then for looking at the ways that they manage their future risk, we just use qualitative data extracted from household surveys and bring together these key themes across the different communities. So in terms of quantifying the resilience, we look at flood resilience here across the 35 riverine communities in Bangladesh. And overall, it's low. So it's averaging at 27%, which is a grade C overall. And when looking at this map, it's also evident that the overall levels of resilience are greatest in the lower Jamuna River region, where the average is 47%. And that's likely due to higher levels of scientific and political attention along this stretch of the river, which also would result in more external support. What's alarming to see here is that in the southern communities along the Kumar River and the Padma River, both of those are averaging at 16%, which is the lowest grade that you can have, and that's an average, so that's quite alarming. And then in terms of riverbank erosion resilience. Here we're showing the 19 communities that are within highly geomorphically exposed regions. So the matrix here shows geomorphic hazard along the top, and then the level of resilience along the left-hand side. And what you can see here is basically that there's a whole range of communities along here, along the matrix, but there's 7 within the red zone. And those are the ones that are alarming. They're actually in the Teesta River, the Northern Jamuna, and the Padma rivers. But in this red zone, basically, it means that they have a high hazard and a low resilience. So it's in these areas that vulnerability is greatest and where temporary or permanent relocation is most likely to be expected. So in terms of strategies for future risk management, communities have been implementing new community planning and organizational groups. So they've formed and created trainings for community resilience action groups, which are self-selected, where community members are nominated by their represented communities. They've also created resilience self-help groups to address the most vulnerable people in each community and provide mutual support to one another. And they've also created groups that join communities with government departments to strengthen the linkages between these communities and service providers to better recover from flood and erosion losses. There's also been a diversification of livelihoods. In particular, they're focusing on better use of fallow land for farming, so fertilizing post-flood land for income-generating activities, which has been really successful in actually ensuring that people continue to make a living after they have had multiple losses from flood and erosion hazards. And then there's also been the implementation and improvement of infrastructure. So they've been raising school buildings, raising homes, improving health services during floodwaters would not contaminate their drinking water. And finally, relocation has also been one of the ways in which community members have been, sorry, I've just been told that I have unstable internet. I hope you can still hear me. But yeah, so relocation has also been one strategy of managing future risk. So the data here has shown that 32% of community members leave their community for more than 1 month per year, with some experiencing temporary outmigration of between 60 and 75%. So community members themselves have said in the surveys that during flood events, most people become unemployed and have to migrate to earn a living. Women become unsafe, and smallholder farmers need to sell their cattle for the crisis of fodder. So overall, you can see from this paper that the resilience of riverine communities in Bangladesh is relatively low. But again, like I said, this is like the worst case situation, and some communities are better off than others. In response to this recognition that their resilience is quite low, these communities have already started initiating a series of committees to better plan and organize for future hazards. And the successes of these have already been evident after the 2020 monsoon floods, with thousands of the poorest and most vulnerable community members provided with social and medical support. So it's important that communities affected by these riverine hazards are at the heart of future responses to both flooding and geomorphic risk, because many studies have shown that communities in riverine Bangladesh have lived there for generations and are already dealing with hazards that are likely to increase in frequency and magnitude in the future. And these types of participatory approaches are fundamental, as there's so much that we can learn from those people that are already experiencing some of these dramatic impacts. So my overall conclusion for the talk today is the fact that with all these ongoing challenges of climate change, urbanization, socioeconomic development, the present day kind of provides this window of opportunity to really rethink how we live with and manage our deltaic environments. And I strongly believe that deltas really do need to be assessed and managed as ever-changing socio-hydromorphological environments. Thanks so much for listening, and I am really looking forward to any questions you may have.
Thank you, Emily. This is fantastic. I think you did such a great job combined our natural science research and societal impact, and that's really really wonderful. Okay, let's open the floor to the audience now. If you have any question, you can go ahead, unmute yourself, and ask Emily directly. Oh, okay. While we are waiting the questions, Emily, I have a question. You show there's such a dramatic change about the channel, the bank erosion, and also you show pretty severe of the salt water intrusion. You know, salinity is just become higher and higher. So, and you didn't talk about that much. What direct cause of that? Like the channel erosion is because of the sediment reduction from the source, or is it because the more human activity, like the swift boat, sometimes they have a more transportation, it costs that kind of in small channel wheel, or I mean, it's just dragging the sand. What's the direct or possible causes?
Yeah, no, it's a good question. And so firstly, in terms of the salinity, so that's been linked with the construction of the Faraka barrage on the Ganges River, which has basically resulted in not enough. So usually there's a lot more fresh water that's going through the Ganges system to then also flush out the salinity in southwest Bangladesh. But with the construction of the Faraka barrage and this diversion of water, then the salinity is not getting flushed out, and so it's moving further inland. Yeah, in terms of the erosion, I mean, so the Brahmaputra River in particular it's a braided channel, so erosion is natural anyway. But in terms of this constant flux, there's also been studies that have kind of linked that to the 1950 Assam earthquake, which mobilized a lot of sediment. So that's why the channel of the Brahmaputra River has also increased in width, because this sediment was being deposited along the Brahmaputra River.
Okay, well, good. So the salinity is not mainly caused by sea level, but instead of the fresh water direct.
Yeah, it's this balance between pushing the salinity front away with fresh water and also the sea level rise. Yeah, but it's mainly linked to fresh water.
Okay, cool.
So, hi, Paul.
Yeah, go ahead. Yeah, Dr. Islam Shahidu. You have a question?
Yes, I have question, comments, many things. However, at this moment, I have one question. She has already mentioned that the polarization in the coastal area, particularly in the southwestern coastal area, we had to give a lot of price for that. We lost our environment, economic loss, environmental loss, and also the geomorphological loss. Tremendous geomorphological changes in the southwestern coastal part because of this polarization. But she has already mentioned, but not given enough stress on that. Government is in the process to implement a delta plan, 2100. Delta plan is a mega project. It will make tremendous morphological change throughout the country. So, and this is again the large scale implementation of the polder project, which had been implemented during the 1960s. So how do you think this mega project, if it is implemented throughout the nation, what will be the future fate of the delta?
Great question. Yeah, I think you're very right that there's a lot of new projects and the Delta Plan as well that are being implemented to better like make these management measures more dynamic. But I mean, it's difficult to tell what the future will look like. And it's also something that I've kind of thought a lot about, is whether, it's already too far gone, because with the polders in the coastal area, this tidal river management of breaking the polders and allowing the freshwater, floodwater with sediment to kind of come in and elevate the land again. This means a lot of relocation of people, and that's very controversial. But I think you're right that there's a lot of work being done, and I just hope, my personal hope is that these kind of more dynamic underlying processes are really incorporated into all of these plans, because this static infrastructure of embankments or walls, it really does change the whole system. And in a deltaic nation like Bangladesh that has so many different processes happening at the same time, when you put in these static infrastructure systems, it just messes with those dynamics. I don't know if that answers your question.
May I have another question to you?
Yeah.
You mentioned the geomorphic process and how the geomorphological changes has impacted the entire economy, entire ecosystem, environment, many other things. So all these problems are very much what I should say. All these hello, can you hear me?
Yeah.
Yes.
Problems are technical, but all these problems are technical problems. But we think the water resource management or even the geomorphic management of the entire GBM delta is political decision of among the stakeholding country, India, Bangladesh, China. What is your comments about the political commitments of these nations?
Yes, that's one of the points that I was kind of trying to make at the end of this review paper, which is the fact that Bangladesh has the unfortunate situation that it's the downstream nation from all of these other countries. So the decisions that are made in China and India and also in Bhutan and Nepal have impacts on Bangladesh, and it is a political decision. And sometimes I also ask myself whether even if Bangladesh has the most amazing sustainable delta plan, it can still be undermined by upstream decisions. So it's very much a political situation. And I think sharing of data, sharing of information, and kind of working together with the other countries would be ideal. And I mean, I know the Mekong River Commission is not perfect, but something like the Mekong River Commission, where you have this joint transboundary management of water and sediment, that kind of system where there's more conversation across countries is what I would hope for.
I think it's very good. Emily, you give a very good answer. Definitely, we need more dialogue, need more collaboration, because this is not a single country river. This is definitely international. Particularly, I agree with you, the downstream, the delta country is suffering because nothing they can do. I mean, and same question, I think Eric Balansky. So Eric is almost 11 p.m. over there. So I'll give you go ahead, ask the question. Thank you for coming here, Eric. Do you want to unmute yourself, or you want? Yeah, go ahead.
Yeah,
Eric.
What will happen to the geomorphology if by 2050 the dams and water diversion are all built in China and in India? How will the rivers change?
Who knows? It's a very big concern. I would think that, I mean, if you want a concrete answer, there's other examples in the world, such as the Mississippi River, where a lot of the Mississippi River has been engineered and now the delta is sediment starved. That might happen, but the amount of sediment going through the system still today is a lot, and it's still stable. So the GBM delta is very effective in redistributing sediment around the delta. But if, you know, if all of those 414 dams are built, it is very, very concerning, very, very concerning.
That's true.
Maybe there are others here that also would like to share thoughts. Steve, you worked with me on this project, so maybe you have any ideas you want to share, please do go ahead. Nice to see you again.
Me too. I was just typing. It was an amazing talk, Emily. It's great to see the connection of the geomorph work that you did in the first paper to the poverty and solutions. Yeah. So one thing about dams is it's one thing to see them all on paper, and when you go to the local projects, they often don't come to fruition. There are a lot of challenges to implementing all of those dams. And so, you know, maybe one saving grace is that many may not be built, and it may take a long time. So there may be chances to have more sensible, balanced strategies.
Yeah, I guess that is good news. a little bit of good news.
You know, actually, Emily, you mentioned about the Mekong River. You know, the Mekong River now only 22 million sediment discharged to the delta. Only 22. Used to be 160, 130, but only now 22. But even 22 to the delta. On the delta, the sand dredge, you know, removed illegal sand mining, removed 40 or 50. So now Mekong actually there's a negative sediment discharge really delivered to the ocean. That's a big problem, big problem over there.
Yeah,
so
yeah.
Eventually, as Eric asked the question, if all the dam, all the thing built 2050, I mean, Bangladesh will possibly lose a big piece of land.
Yeah, I think the one difference with the Mekong River, from what I remember, I studied the Mekong River in my undergraduate, and from what I remember, the Mekong River, the dams are predominantly on the main branch of the Mekong River, whereas in the GBM system, where the dams are at the moment and where they're planned, they're on smaller tributaries. So it might not be as severe as the Mekong River's impacts there, but of course the accumulated impact from all of the smaller dams on the tributaries also have a huge impact overall on the distribution of sediment that's actually getting to the delta and keeping it afloat.
Okay. Michael, you have any comments? Anything you want to say? Oh, you muted. And
no,
anyway, you just returned from Bangladesh.
I just returned. I was surprised. I actually ran into a number of places that have switched from shrimp farming back to rice farming. I saw, but yeah, and part of looking at the global scale or the Bangladesh scale is there are, so many differences in terms of what's going on sort of in the Chars and the Jamuna versus along some of the rivers are in the Southwest, to try to, pull apart what the actual hazards and responses for each are, because they're so different.
Yeah, exactly. And it was a huge challenge to try and put it all together into one paper for that first paper. But in terms of responses, I would say it's almost impossible to kind of put together a series of responses that address all the different challenges, because they all range not only in terms of the impacts, but also in terms of scale. So yeah, that's why for the final part of the PhD, I've just decided to focus on riverine communities that are all kind of experiencing similar hazards at similar scales.
Yeah.
Very good. Okay, if no any other questions, so Emily, did you see the chat?
Yes, I saw. Yeah.
Yeah. So Steve
Steve had to go.
Okay. Okay. So I think now is here is 10 o'clock in the East Coast US. So thank you, Amelie, very much. I also need to rewatch of your presentations. So many detail. We have so many information in the chart. I mean, so it's wonderful. This community, we definitely need that portion. And so thank you. I'll see you next week, guys. Okay. So long.